Welcome to this problem walkthrough. Today, we will explore LeetCode problem number 1541, titled Minimum Insertions to Balance a Parentheses String. In this session, we'll break down the problem, analyze the solution approach, and discuss the algorithmic complexities. Let's dive in. In this problem, we are given a string S that consists only of opening and closing parentheses, represented by the characters and. Our goal is to determine the minimum number of insertions required to make this string balanced. Now, a balanced parentheses string must meet three conditions. First, every opening parenthesis must have a corresponding closing parenthesis. Second, each closing parenthesis must close the most recently unmatched opening parenthesis. Finally, every opening parenthesis must be paired with exactly two closing parentheses in order to form a valid balanced string. The input is a string S with a length between 1 and 100,000 characters, and the output is an integer representing the minimum number of insertions required to balance the string. Let's look at the first example. Here, the input string is S equals. The output is 1, which means we need one insertion to make the string balanced. To see why, consider the current string structure. The first two opening parentheses appear to be matched correctly with closing parentheses, but at the end, there is an extra closing parenthesis. To balance the string, we need to insert one more closing parenthesis at the end, making it. This new string satisfies the condition that each opening parenthesis is paired with exactly two closing parentheses. Now, consider the second example where the input string is S equals. The output in this case is 0, meaning no insertions are needed. This is because the string is already balanced. The first opening parenthesis is paired with two closing parentheses, and there are no unmatched parentheses in the string. For the third example, the input is S equals. Here, the output is 3. To balance the string, we need to insert one opening parenthesis at the beginning, making it. Then, we need two closing parentheses at the end, resulting in. This gives a total of 3 insertions. In the fourth example, the input string is S equals. The output is 4, which represents the number of insertions required to make this string balanced. To achieve this, we need to add 4 closing parentheses at the end of the string, resulting in. This way, each opening parenthesis is matched with exactly 2 closing parentheses. It's important to note that the constraints of the problem require us to handle strings of up to 100,000 characters efficiently, with a time complexity of O(n). This means our solution needs to process the string in a single pass, keeping track of unmatched parentheses and the number of insertions needed. Additionally, edge cases such as strings with only opening or closing parentheses, alternating patterns, or very short strings must be carefully considered when designing the solution. To solve the problem of determining the minimum insertions needed to balance a parentheses string, we must first understand what it means for a string to be balanced. A balanced string satisfies 3 key rules. Every opening parenthesis must have a corresponding closing parenthesis, the closing parenthesis must appear after its matching opening parenthesis, and each opening parenthesis must be closed by exactly 2 consecutive closing parentheses. With these rules in mind, we can start exploring different approaches to solve the problem effectively. One straightforward way to solve this problem is with a brute force approach that simulates the process of balancing the parentheses by reconstructing the string. The intuition here is simple. We traverse the string character by character, keeping track of the balance between opening and closing parentheses, while ensuring that each is closed with. Whenever we encounter an imbalance, we explicitly insert the required parentheses. To implement this, we maintain a counter for open, track how many are needed, and make insertions whenever there's a mismatch. Although this approach runs in O(n) time due to the linear traversal and operates in O(1) space by modifying the string in place, it can be inefficient for large inputs because of the repetitive operations involved. Instead of modifying the string directly, we can use a more structured approach with a stack-like mechanism to track unbalanced parentheses. The key idea here is recognizing that each must eventually pair with. By tracking the state of unclosed and unmatched, we can calculate the required insertions in a single pass. Practically, this means we initialize 2 variables, one for open and another for unmatched. As we traverse the string, we increment the open counter for each and evaluate whether can close and open. If not, we increment the unmatched counter and determine the necessary insertions. Once the traversal is complete, we account for any remaining open to finalize the count. This method also runs in O(n) time an O(1) space, but it avoids direct string modification and handles edge cases like strings with no opening or no closing parentheses. Building on the stack-like approach, we can simplify further with a greedy one-pass optimization. Instead of using a stack or explicitly tracking unmatched, we rely on two counters, one for unclosed, and another to tally the required insertions. As we process the string, every increments the open counter, while a attempts to decrement it, indicating a match with an open. If no match is possible, we increment the required insertions to account for the imbalance. At the end of the traversal, any leftover open is handled by adding double the count to the total insertions, since each requires to balance. This method retains the same O(n) time an O(1) space complexity but is easier to implement and more efficient overall. One of the key insights that made this approach work was realizing that each requires exactly to be balanced. The greedy one-pass approach proves to be the most effective solution for this problem due to its simplicity and optimal resource usage. By processing the input in a single traversal and using constant space, it strikes the perfect balance between clarity and efficiency. Additionally, replacing stacks or string reconstruction with counters made the solution both elegant and fast. While brute force might be intuitive for beginners, its inefficiencies with larger inputs make it less practical. The greedy method, on the other hand, allows us to make local decisions for each character without revisiting earlier parts of the string, making it scalable and robust for all inputs. Overall, this approach stands out as the best strategy for solving the problem effectively. In this problem, we are tasked with finding the minimum number of insertions required to make a parentheses string balanced. A balanced string must satisfy three key conditions. First, every opening parenthesis must have a corresponding closing parenthesis. Second, each closing parenthesis must be part of a valid pair. And third, the pairs must be in the correct order, meaning an opening parenthesis always comes before a closing parenthesis. However, there is an additional twist here: each opening parenthesis requires exactly two closing parentheses to form a valid pair. For example, the string is considered balanced, whereas is not. This constraint adds a layer of complexity to the problem, making it critical to ensure that we handle both unmatched and incomplete pairs as we work through the string. To solve this problem, we use a greedy approach that processes the string in a single pass while keeping track of the balance of parentheses. The first step in the algorithm is to initialize two counters. The open_needed counter keeps track of the unmatched opening parentheses, while the insertions counter records the total number of insertions needed to balance the string. Next, as we iterate through the string character by character, we evaluate two main cases. When we encounter an opening parenthesis, we increment open_needed because each requires two closing parentheses to become balanced. On the other hand, when we encounter a closing parenthesis, we first check if there is an unmatched available. If there is, we decrement open_needed since this closing parenthesis can help balance one of the unmatched we have seen so far. If no unmatched is available, we increment insertions by 1, as we need to insert an opening parenthesis to balance this closing parenthesis. Additionally, because each requires 2, we also ensure that every closing parenthesis is part of a valid pair by checking if it is the second in the pair. If a closing parenthesis is not part of a valid pair, we increment the insertions counter again to add the missing closing parenthesis needed to complete the pair. After finishing the traversal of the string, we handle any unmatched that remain. Since each requires 2 to form a valid pair, we add 2 open_needed to the insertions counter to account for these unmatched parentheses. Finally, the value of insertions gives us the minimum number of insertions required to make the string balanced. The key insights here are the use of a greedy method, which enables us to make corrections as we traverse the string, and the careful handling of closing parentheses to ensure they always form valid pairs. This approach minimizes the number of insertions and avoids the need for multiple passes through the string. By the end, we address both unmatched and efficiently, ensuring the string is fully balanced. To implement this algorithm, we rely on simple data structures, 2 integer counters, open_needed and insertions, which allow us to track unmatched and the total number of insertions required. Processing the string in a single traversal ensures an optimal time complexity of O(n), where n is the length of the string, and a space complexity of O(1), since we use constant extra space. It's also important to consider edge cases that test the algorithm's robustness. For instance, an empty string is already balanced and requires no insertions. A string with only opening parentheses, such as, will require 6 insertions, as each needs 2. Similarly, a string with only closing parentheses, like, will require 4 insertions to balance. More complex cases, such as interleaved parentheses in, challenge the algorithm to correctly balance both unmatched and, as they occur in sequence. By addressing these cases, the algorithm demonstrates its correctness and adaptability. To better understand how the algorithm works, let's walk through an example with the input string. We start with open_needed and insertions both initialized to 0. As we process the first character, we increment open_needed to 1. The second character increases it further to 2. When we encounter the first, we decrement open_needed to 1, as this balances one of the unmatched. The next decrements open_needed again to 0, completing another pair. When we reach the third, there are no unmatched available, so we increment insertions to 1 to add an opening parenthesis before this. We then increment insertions again to 2 to complete the pair for this. Moving on, the next increments open_needed to 1, and the following increments it to 2. At the end of the string, we still have 2 unmatched. Since each requires 2, we add 2 open_needed, which is 4, to insertions. This brings the total number of insertions to 6. Thus, the minimum number of insertions required to balance the string is 6. Here, we begin by defining the min_insertions function within the solution class, which takes a string s as input. We initialize 2 variables, insertions, to count the number of insertions needed, and open_count, to track unmatched opening parentheses. We then start iterating through the string using a while loop. If the current character is an opening parenthesis, we simply increment open_count to indicate that it is unmatched. However, if the character is a closing parenthesis, we need to check whether it forms a pair with the next character. If the next character is also a closing parenthesis, forming, we handle 2 cases. If there are unmatched opening parentheses, we decrement open_count to pair the with one of them, otherwise, we increment insertions to add a virtual opening parenthesis to make the e valid. We then skip the next character since it has already been processed. If the current closing parenthesis isn't part of a pair, it means it stands alone. In this case, we increment insertions to add a virtual closing parenthesis, creating a valid. If there are unmatched opening parentheses, we decrement open_count to pair this single closing parenthesis with one of them. Otherwise, we increment insertions again to insert an opening parenthesis before handling the itself. After processing all characters in the string, any unmatched opening parentheses remaining in open_count will each require 2 closing parentheses to balance them out. We account for this by adding open_count *2 to the insertions total. Finally, we return the total number of insertions required to balance the string. Here, we begin by defining the method min_insertions, which takes a string s as input. We initialize 2 variables, insertions, which will keep track of the number of insertions needed to balance the string, and openCount, which tracks the number of unmatched opening parentheses. We then use a while loop to iterate through each character in the string. If the current character is an opening parenthesis, we simply increment the openCount since it represents an unmatched opening parenthesis. If the current character is a closing parenthesis, we check if it is part of a pair. To do this, we look ahead to the next character, ensuring it exists and is another. If we find such a pair and there is at least one unmatched opening parenthesis, we decrement openCount to match this pair with an opening parenthesis. However, if there are no unmatched opening parentheses, we increment insertions to simulate inserting an opening parenthesis to match this pair. After handling the pair, we skip the next character by incrementing I. If the closing parenthesis is not part of a pair, it means we need one more closing parenthesis to complete the pair, so we increment insertions accordingly. Now, if the unmatched closing parenthesis needs to be paired with an opening parenthesis, we first check if there are any unmatched opening parentheses by looking at openCount. If openCount is greater than 0, we decrement it to account for matching this closing parenthesis with an opening parenthesis. Otherwise, we increment insertions to simulate inserting one opening parenthesis before this closing parenthesis. Once all characters have been processed, any unmatched opening parentheses still left in open count will each require 2 closing parentheses to balance. Thus, we add open count *2 to insertions. Finally, we return the total insertions value, which represents the minimum number of insertions required to balance the parentheses string. To solve this problem, we start by initializing 3 variables. The insertions variable keeps track of how many additional parentheses we need to add to make the string balanced. The open_count variable tracks the number of unmatched opening parentheses, and I is our index for traversing the string. Looking at the first character, S0 is an opening parenthesis, so we increment open_count by 1. This means we now have 1 unmatched opening parenthesis. We then move to the next character. At S1, we encounter another opening parenthesis. Once again, we increment open_count by 1, bringing the total to 2 unmatched opening parentheses. With this, we proceed further through the string. Next, we process S2, which is a closing parenthesis. Since this is a single, and not part of a pair, we need to add another closing parenthesis to balance it. Therefore, we increment insertions by 1. At the same time, we can match this closing parenthesis with one of our unmatched opening parentheses, so we decrement open_count to 1. Moving forward, at S3, we encounter another closing parenthesis, but this time it is part of a pair. By looking ahead to S4, we confirm this. We match this pair with one of the unmatched opening parentheses and decrement open_count to 0. Since we processed both S3 and S4 as a unit, we skip S4 and increase I to 5. At this point, we have reached the end of the string. With no unmatched opening parentheses left, no additional insertions are required. The final answer is insertions equals 1. Now we analyze a new example where the input string is S equals. Just like before, we start by initializing insertions to 0, open_count to 0, and I to 0. Looking at the first character, S0 is a closing parenthesis. Since it is a single, and there are no unmatched opening parentheses to pair it with, we need to add an opening parenthesis to balance it. We increment insertions by 1. Additionally, this single itself needs another closing parenthesis to form a complete pair, so we increment insertions by 1 again, bringing the total to 2. We then move to the next character. At S1, we encounter an opening parenthesis. We increase open_count by 1 to indicate that we now have 1 unmatched opening parenthesis. With this, we continue to the next part of the string. At S2, we find a closing parenthesis. Since this is a single, and not part of a pair, we need to add another closing parenthesis to balance it. Thus, we increment insertions by 1, bringing the total to 3. We can also match this closing parenthesis with the 1 unmatched opening parenthesis we have, so we decrement open_count back to 0. Moving to S3, we see another closing parenthesis. Again, this is a single, so we need to add both an opening parenthesis and another closing parenthesis to balance it. This means we increment insertions by 2, bringing the total to 5. Finally, we reach the end of the string. Since there are no unmatched opening parentheses, no additional insertions are required. The final result is insertions equals 5. In this final example, the input string is S equals. As always, we begin by initializing insertions, open_count, and I to 0. At S0, we encounter an opening parenthesis, so we increment open_count by 1, indicating 1 unmatched opening parenthesis. We then move to S1, which is another opening parenthesis. Incrementing open_count again, we now have 2 unmatched opening parentheses. At this point, we reach the end of the string. Each unmatched opening parenthesis requires 2 closing parentheses to balance it. Since open_count is 2, we add open_count *2 to insertions, resulting in insertions equals 4. Therefore, the final answer for this example is insertions equals 4. The time complexity of this solution is O(n), where n is the length of the input string. This is because the algorithm processes each character of the string exactly once using a while loop. Inside this loop, the operations performed are all constant time. These include checking the current character, updating counters such as open_count and insertions, and performing comparisons like whether the next character exists or matches a closing parenthesis. Even when the algorithm detects a pair of closing parentheses and skips the next character, the total number of operations remains proportional to the size of the string. As a result, the time complexity is linear, or O(n). The space complexity of the solution is O(1), meaning it uses constant space regardless of the size of the input string. This is because the algorithm only uses a few integer variables, like insertions to count the number of insertions needed, open_count to track unmatched opening parentheses, and I for iteration. These variables take up a fixed amount of memory and no additional data structures such as arrays, stacks, or hash maps are used. Furthermore, the input string is treated as read-only, so no extra space is allocated for processing it. Therefore, the memory usage remains constant, leading to a space complexity of O(1). To compare, a brute force approach might involve explicitly constructing a balanced string by iterating through the input and inserting characters when necessary. This would not only require additional space to store the intermediate string but would also result in a space complexity of O(n). While the time complexity would remain O(n) due to traversal, the extra space needed for the output makes it less efficient. In contrast, the optimized approach avoids creating a new string altogether. By using counters like open_count and insertions, it calculates the required insertions directly while processing the input string in place. This eliminates the need for auxiliary data structures, achieving both O(n) time complexity and O(1) space complexity. In terms of best, average, and worst-case scenarios, the time and space complexity remain consistent. In the best case, if the string is already balanced, such as, the algorithm still processes each character exactly once, resulting in O(n) time and O(1) space. For an average random string, the same operations are performed for each character, maintaining O(n) time and O(1) space as well. In the worst case, where every character requires an insertion, like a string of only closing parentheses, the algorithm still processes each character once. Each operation, whether it's a comparison or a counter update, is performed in constant time. Since the algorithm iterates through the string linearly and uses no extra memory aside from the counters, the time complexity remains O(n), and the space complexity O(1), regardless of the input size. When solving this problem, there are several common mistakes to watch out for. First, remember that a balanced parentheses string requires two closing parentheses for each opening parenthesis. For example, if you have 3 opening parentheses you'll need 6 closing parentheses to balance it, not just 3. Forgetting this rule can lead to miscalculations in the number of insertions required. Another common error happens when handling consecutive closing parentheses. If you encounter, this is already balanced and doesn't need any insertions. Misidentifying it as needing an extra could lead to overcounting. Additionally, it's important to reset your counters after balancing a group of parentheses. For instance, in a string if you don't reset after the first group, you might end up double counting or misaligning your calculations for the next group. Finally, don't overlook edge cases such as empty strings, strings without opening parentheses or strings with only closing parentheses These scenarios require careful handling to ensure your solution works for all possible inputs. Inefficient solutions are another pitfall to avoid. Using nested loops to check for balance can quickly lead to an O(n)² solution, which is impractical for larger inputs. Instead, focus on simplifying your logic. Start by recognizing that balancing parentheses involves 2 main tasks: ensuring every opening parenthesis has 2 closing parentheses and managing any surplus closing parentheses. Breaking the problem into these parts can make it much more approachable. For edge cases, it's always a good idea during an interview to clarify how these should be handled, such as empty strings or strings containing only closing parentheses. Another key point to emphasize is optimal complexity. A single pass through the string, achieving an O(n) solution, demonstrates both efficiency and a strong grasp of the problem. As you work through your solution, clearly communicate your thought process to the interviewer. Explain how you're tracking unbalanced opening parentheses and surplus closing parentheses, and use examples to illustrate how your logic handles different scenarios. This problem also shares similarities with other related problems, which can help you build a stronger foundation. For instance, problem 20, valid parentheses, asks you to determine if a string of parentheses is valid. Problem 921, minimum add to make parentheses valid, is closely related since it also focuses on finding the minimum number of additions needed to balance a string. Problem 678, valid parenthesis string, introduces an extra layer of complexity with wildcard characters that can represent either, or an empty space. Finally, problem 1249, minimum remove to make valid parentheses, focuses on removing invalid parentheses to create a valid string. Exploring these problems can deepen your understanding of balancing parentheses. When it comes to solving this problem, one approach is brute force, where you try all possible insertions to balance the string. However, this method is highly inefficient, with a time complexity of n squared, or worse, making it impractical for larger inputs. Another approach is using a stack to track unbalanced parentheses. While intuitive, this method requires extra space proportional to the input size, making it less optimal compared to space-efficient methods. The most efficient approach to this problem is the greedy counter method. This involves maintaining two counters as you traverse the string. One counter tracks the number of unbalanced opening parentheses, while the other tracks surplus closing parentheses. By processing the string in a single pass, you can efficiently determine the minimum insertions required to balance it. This method has a time complexity of n and a space complexity of 1, making it the most optimal solution. However, implementing the greedy approach requires attention to detail. It's essential to carefully manage your counters to avoid common mistakes, like forgetting to account for the need for two closing parentheses per opening parenthesis or mishandling consecutive closing parentheses. With proper implementation, this method not only ensures correctness but also demonstrates your ability to write efficient, scalable code. Great job! We've successfully solved the problem and explored its solution details. Remember the key concepts and practice similar problems to strengthen your understanding. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!